guys, how are you doing? How are you doing? It's your last lecture. It's last lecture, yes? So then probably you are a bit tired, but let's try to find a little bit more of energy and both here. So we continue our discussion of kinematics, and first we will shortly recall what we discussed previous time. So we discussed motion along axis x, like one dimensional case, motion along a straight line. And in that case, in order to define the direction of motion, it was enough to set the sign of displacement, positive or negative. So that was easy. We should not deal with any vectors. In the scope of this model, we introduce concepts of velocity and acceleration, which are instantaneous velocity and acceleration. So they give us the exact value of these parameters at any moment of time. And that is the key requirement to know in order to proceed further and derive so-called kinematic equation, which describes position of an object at any moment of time in the scope of some given system of vectors. Last time it was straight line, some axis x. We derive this kinematic equation considering the condition of constant acceleration, and also considered some transformation of this kinematic equation when we substitute time, t, as independent parameter, and could express position, like velocity, as a function of position. Or in the contrary, you can express, obviously, position as a function of velocity, avoiding using time as independent parameter, which can be quite useful. So that was done for one-dimensional case. Today we make one step further and consider two-dimensional case when we already have to deal with vectors, because initial position will be given by position vector. Then we will have some velocity vector and acceleration vector. So in order to know how to work with them, we will introduce again velocity, instantaneous velocity and accelerations, but already in a vector form, and write the kinematic equation, general kinematic equation in vector form, which allows us to describe position of a body, an object in space at any given moment of time. So that is our goal, and we will also consider some example of this motion in two-dimensional space with constant acceleration. So let us start. We have already a system of coordinates. We have already not only axis x, but also axis y. Let's consider some trajectory of motion. And here we consider point 1. So let's say it's some initial position of the body. And how we define this position, we have so-called position vector. So that will be R1 vector. Let's say after some time interval, this body will move from point 1 along this trajectory to point 2, which is described by its position vector, R2 vector. So now we have two position vectors, but we also have this initial and final point, which we consider in the scope of this consideration, this example. And we can also introduce here a displacement vector, which connects initial and final position of the body. And that will be delta r, change of position vector. So this is maybe let's go for colorful version. So this is displacement vector delta r vector. So now let us introduce the concept of instantaneous velocity vector, which is required to describe our motion in the two-dimensional space. So in general, we can write that v vector, instantaneous velocity vector, will be equal to limit delta t approaches to 0, delta r vector divided by delta t. And that is nothing else. That is nothing else as the first derivative of displacement vector dr over time. So that is definition of velocity vector in multi-dimensional space. Doesn't matter if it's two or three-dimensional space. And also we need to introduce another important parameter, which is instantaneous acceleration. So a vector is equal to the limit delta t approaches to 0. Here we have delta v vector divided by delta t. And it can be represented as first derivative of velocity vector over time, or second derivative of position vector, like displacement vector, with respect to time. So it will be dr vector d square r vector dt square. So that is definition of instantaneous velocity and acceleration vectors. And now we can already proceed with answering the main question of kinematics of motion in two and three-dimensional space. We want to know position vector as a function of time at any moment. So that is our goal. We need to have this equation. So how we do this? In order to make our life easier, you should recall from our previous discussion, we had this guys unit vectors, which allow us to split any vector to two components when we are talking about two-dimensional space along axis x and along axis y. So that's obviously what we want to do, because then it's easy to do calculations with such vectors. So we can represent our position vector as sum of two vectors. It will be x times I unit vector plus y times j unit vector. Now, in the same manner, we can proceed further with the definition of velocity vectors and acceleration vectors. So, for instance, for velocity vector, we know that it is first derivative of position vector over time, and that is dx over dt times I unit vector plus dy over dt times j unit vector. So what are these guys? These are projection of velocity vector on axis x and y. So we can represent them as vx times I unit vector plus vy times j unit vector. Now we have these values vx and vy. So keep in mind that they are along a straight line. Vx is velocity along x, vy along axis y. So we already know how to describe velocity of motion along a straight line with constant acceleration, because we discussed it earlier. So we can now extrapolate this knowledge towards two-dimensional case, but specifically when we discussed two components of the velocity vector along axis x and axis y. So for this Vx and Vy, we can write that Vx is equal to Vx naught, some initial value for this x component of velocity vector, plus ax times t. And here will be Vy equal to Vy naught plus ay times t. So that is our expression, which we borrow from previous discussion. And that is true for each of these projections. Also, what is important to mention here, if we have constant acceleration vector, a vector is equal to constant, then ax and ay, they are also constant. They don't change over time. So we can use just constant values for this acceleration projection of acceleration vector along axis x and y. So now let us substitute these expressions here and this one here in order to get the general equation for velocity vector. So velocity vector is equal to Vx naught plus ax times t times I unit vector plus Vy naught plus ay times t times j unit vector. So now let us open this parenthesis and group velocity to velocity and acceleration to acceleration. So that will be Vx naught times I unit vector plus Vy naught times j unit vector plus now acceleration time. It will be ax times I unit vector plus ay times j unit vector, and that is times t. So now we see that we have actually two components of this velocity vector. One component here is v naught vector, and another component is a vector. So eventually we can write that velocity vector v will be equal to the initial velocity vector v naught plus a vector times t. So that is for constant acceleration vector. And this is the general form which describes the time dependence of velocity vector. And we can also represent it graphically. So let us consider a system of coordinates x and y. Here will be our initial velocity vector, v naught vector. Here will be our acceleration vector times t. And obviously, as a sum of these two vectors, we will get some resultant vector, which is our velocity vector v. And of course, that is just graphical representation, but when we do any calculations, we obviously will operate with these unit vectors because it is convenient. Never doesn't matter what we do, add or multiply vectors later or whatever. So we now have information for velocity vector, and our next task is to get the same expression for position vector. So we remember from previous lecture that we derived this kinematic equation for motion along straight line with constant acceleration. So how did it look? So we have x equal to x naught, initial position, plus what is next? V naught, initial velocity, V naught times t, plus a times t squared divided by 2. Good. So we have this equation, and that is actually true for the projection of position vector on axis x. However, since we have two coordinates now, two-dimensional case, we also need to write it for y component. So it will be y naught plus that here it actually, we need to modify it a little bit. So here we need to consider x naught and ax. And here it will be vy naught times t plus ay times t squared divided by 2. So that is true for the projection of position vector on axis y and x as a function of time. So now let us introduce it already in a vector form. When we have position vector as a function of time, that will be equal to, as we mentioned earlier, x times I unit vector plus y times j unit vector. That is equal to, instead of x, we substitute this expression. So it will be x naught plus vx naught times t plus ax times t squared divided by 2 times I unit vector plus y component. So it will be y naught plus v y naught times t plus a y times t squared divided by 2. And divided by, so multiplied by j unit vector. Now again, we open parentheses and group initial position, initial velocity, and acceleration vector. So we have x naught times I unit vector plus y naught times j unit vector plus now component from initial velocity. That will be vx naught times I unit vector plus vy naught times j unit vector times time t plus term originated from acceleration. It will be ax times I unit vector plus ay times j unit vector times t squared divided by 2. So eventually we have here is our initial vector, position vector, r naught vector. This guy will be our initial velocity vector, v naught vector. And this is our acceleration vector, a. So eventually we can write that position vector as a function of time is equal to initial position vector plus initial velocity vector times time plus our constant acceleration vector times time squared divided by 2. So this is the kinematic equation in the vector form. So it can be applicable to all cases when we have motion in different from motion along a straight line. So if there are 2 or 3 directions, like dimensions, we can apply this concept and determine position vector for an object at any given moment of time. So now let us consider, actually we can also show it graphically, similar to velocity. Let us show it here. We have two axes, x and y. So this will be initial position vector r not zero, r not vector, and here we have term originated from initial velocity vector v naught vector times t, and additionally we have acceleration vector times t squared divided by 2. So eventually our new position vector r vector at time t will be given as sum of all these three vectors together. So that's how we define in graphical form. But again, any calculations are first done in the form when we deal with unit vectors, because that's convenient. So now let us consider some example of motion of an object in 2 dimensions with constant acceleration. So that is so-called projectile motion, when we have a projectile moving with some initial velocity at some angle with respect to axis x, and in that case we have constant accelerations because we don't consider, like, neglect with any drag force of air. So we have constant acceleration, which is acceleration of free fall pointed downwards, means in the opposite direction to the positive direction of axis y. So let us consider this in more details and start with the quantifying the conditions. Hello. So maybe let us consider this process in more details. This will be x, y. Here will be some projectile trajectory. And it starts from point 0, so it's from the origin of the system of coordinates. We have some vector v naught vector, which is initial velocity vector, at some angle theta to the horizon. Obviously, this vector will have some projection on axis x and y. So we will have vx naught, and here will be vy naught at the initial moment of time. So if we move to point, let's say this point will be A, let's call it amplitude point, where we reach the maximum height of the trajectory over the horizon, what will happen? Taking into account that our acceleration g is pointed downwards, it will affect only y component of our initial velocity vector. X component will remain constant. So means that at maximum point of this trajectory, we will not have any component of like y component of velocity, but it will be still vx naught. And obviously, if we let this projectile flow further, it will go downwards. So at some point, let's say B, here will be the same component of Vx naught projection, because it doesn't change, it stays constant. And here will be some V y, let's call it B, projection of the velocity vector in this point B. It will be b vector on axis y, which it will gain by accelerating under free fall conditions, but it will be already in the opposite direction. So initially, component x, y, vy was along axis y, and now it goes in the opposite direction because it starts to fall down. So taking this into account, we can write down the general expression for position vector r as a function of time, r naught plus v naught vector times t plus a vector times t squared divided by 2, and consider that r naught is equal to 0 because we start from this projectile motion from the origin of the sinking point. Then we don't need to have this term, it will be equal to 0. So now let us consider v naught vector, and in particular its projection on axis x and y. So we can write that vx naught is equal to v naught, means magnitude value of the initial velocity vector, times cosinus theta, which is angle between velocity vector and horizon. And what is important, this remains constant. It doesn't change over time. So obviously for vy naught, we can write that v naught magnitude of the velocity vector times sinus theta. This is not going to be constant because along the same direction we have this acceleration of free fall. Now let us write the expression for velocity along axis y as a function of time. So we can write that vy is equal to vy naught plus a times t. A in our case, until, so this expression will be valid until we reach point A, maximum point of the trajectory, amplitude, height. And instead of a here, we can write minus g because that is our acceleration aligned along axis y. So here we can write that it will be vy naught minus j times t. If we consider already vy as y component of the velocity vector after point A, so when projectile moves further from point A, that will be just minus g times t because we don't have any initial velocity in y direction at point A. So we consider first the equation for y components of our velocity vector before it reaches maximum point of trajectory, then it stops, it doesn't move. It stops means it doesn't move along axis y, it reaches highest point. It's still moving along axis y, this vx doesn't change, it remains constant. But y component is equal to 0, and then it just starts to fall down. So now, taking into account this general description of the system, we can proceed further and consider some y and x ranges of this projectile motion. So let's see what it is. If we have some projectile, axis x and y, here is our velocity vector, angle theta, point A, amplitude point, and let's consider also point F, like final point of this trajectory. So here is the height, of the trajectory. So it's y range of the trajectory, and here is the x range of the trajectory. Let's call it r. So that is the maximum length, which, like the length of the project motion along axis x. So let us define these parameters. Let's start from h. We know that at point A, let us say that time when this projectile reaches point A will be equal to, TA. So to define it specifically, it will be TA. So in time TA, projectile will reach its maximum height. Then we know that Vy at TA will be equal 0. So it will reach maximum height and will not move further along axis y. So taking into account this equation and substituting TA instead of t, we can write that 0 is equal to Vy naught minus g times t. We need to recall that Vy naught is actually v naught, magnitude of the initial velocity vector, times sinus theta, angle between velocity vector and horizon. So that will be v naught times sinus theta minus g times ta. Here we need to write ta because it's specific time when projectile reaches the highest point of the trajectory. So based on this equation, we can express TA, this moment of time, as v naught times sinus theta divided by g. So that is this time when projectile reaches the max point defined by point A as a function of initial magnitude of initial velocity, its orientation with respect to horizon, and acceleration of free fall. So now we can move to the kinematic equation of this projectile along axis y. We know that y is equal to y naught plus v y naught times t plus acceleration times t squared divided by 2. Instead of a, we can substitute minus g. So that will be y naught plus v y naught times t minus g times t squared divided by 2. We also know that y naught is equal to 0 because it starts from the origin of the system of coordinates. And we know that Vy naught is given by V naught times sinus theta. So we can now substitute here also expression for TA. And that will be our maximum height, because if it defines the position of our object with respect of axis y, we know that at time ta we have the highest point A, so this coordinate of point A along axis y will be h, the highest point of the trajectory. Now let us substitute instead of Vy naught and instead of Ta their expressions. So we can write that h is equal to v naught, magnitude of the velocity vector, times sinus theta times TA. What is TA? Is given here. So it will be V naught times sinus theta divided by G. Then we have additional component originated from free fall acceleration. So it will be G divided by 2 times TA squared. So it will be V naught times sinus theta divided by G in second power. Okay, so now let us open this parenthesis. So keep in mind here we cancel out with this G because it's in the numerator. And we have the following. We have V naught square times sinus square theta divided by G minus V naught square sinus square theta divided by 2G. So what we have eventually is just 1/2 of V naught square times sinus square theta divided by G. So this is our expression for the maximum height in trajectory. And now we can go further and use this also in consideration for time TA for the purpose of determining this x range r, the length of the trajectory along axis x. So let us come back to our plot and think about this. If it takes time TA from initial moment of time t0 to reach for projectile from initial point, reach the point A in the top of the trajectory, that will be the same time if we let this projectile move further to reach the final point. So it took some time to stop the projectile motion along axis y because of free fall acceleration, and then we have just free falling this projectile further along axis y, and final point of the trajectory will be reached in the same interval of time. So if we introduce some time tf, means time when projectile reaches the final point of the trajectory, that will be equal to ta times 2. So we will have twice longer tf than ta. So let us write it here. Tf will be equal to 2 ta, and we know that ta is given as v naught times sinus theta divided by g. So it will be 2 times v naught sinus theta divided by g. So that is for time when the projectile reaches the final point of the trajectory. Now we consider the x projection of the position vector. So we know that it's x equal to x naught plus vx naught times t plus a times t squared divided by 2 ax. So in this case, what we have, x naught is equal to 0 because it starts from the origin of system of coordinates. Vx naught, we know what is Vx naught, that is equal to V naught, magnitude of initial velocity vector, times cosine of angle theta, times t, and Ax, in this case, what will be Ax? what do we put instead of ax?
Plus G. Multiplied by.
So let us come back to our original figure here. See it? Yes. So you see this G is aligned perfectly along axis y, means its projection on axis y will be minus G, and projection of vector G on axis x will be 0 because it's perpendicular.
Sine theta. G sine theta.
No, sine theta, so you see, this is with the velocity, initial velocity vector, that guy is oriented at some angle theta. That's why we have projection on both axis x and axis y. If velocity vector is oriented vertically, like perpendicular to axis x, then we would not have any projection on axis x, it would be just projection on axis y. So we have similar case for g, acceleration of freefall, is oriented downwards parallel to axis y. So that's why all projection of, it has only projection on axis y. And axis x, its projection is equal to 0. Means there is no acceleration of a change of velocity component along axis x. That's why we mentioned that Vx remains constant. It doesn't change over time. So once we discuss this part, we can come back and write that Ax is equal to 0 because projection of acceleration, free fall acceleration vector on axis x is equal to 0. So eventually we have position x equal to v naught times cosine theta times t. So that is the form of kinematic equation for this projectile along axis x. And now if we want to know this maximum range for x direction, we need to consider time tf, time when our projectile, it's not here, when our projectile reaches the final point of the trajectory. So we can write that r, length of the trajectory along axis x, will be equal to v naught, magnitude of initial velocity vector, times cosinus theta times tf. And we know that tf is given by this equation. So we can substitute it here. So let's write here. It will be v naught times cosinus theta times 2 times v naught times sinus theta divided by g. So what do we have here? We have v naught square times 2 cosinus theta times sinus theta divided by g. So here, this term, we can use trigonometric identity, and that tells us that 2 times cosinus alpha times sinus alpha is equal to sinus 2 alpha. So we can use this identity in order to simplify our equation. So that will be v naught square times sinus 2 theta divided by g. So that is the expression for the length of the trajectory along axis x. And now we can take a look at this equation. So the thing is that if we want to find the angle which will result in the maximum x range, it's quite clear from this equation what we need to do. So sinus doesn't matter of which angle, its maximum value is possible is unity. So when it will reach unity? When argument of sinus is equal to which angle? Sinus 90 degrees, yes. So that means that 2 times theta should be equal to 90 degrees in order to get maximum value for x range. And from here, automatically we get that the angle of orientation of initial velocity vector of the projectile should be arranged at 45 degrees with respect to the horizon. So that is the condition which will result in the maximum x range for the projectile trajectory when we consider projectile motion as motion in two-dimensional space with constant acceleration. So let us summarize. Today we kind of continued our previous discussion and introduced in a vector form velocity and acceleration vectors. So that case allows us to quantify position of an object in a system with many dimensions, 2 and more, like 2 and 3. In order to do some calculations, we obviously need to split position vector, initial position vector, velocity vector, and acceleration vector into components by applying these unit vectors. But also we have shown how it looks in a vector form when we kind of end up different vectors originated from different contributions, the initial position vector, velocity vector times initial velocity vector times time, and acceleration vector times t squared divided by t. Of course, it's in the scope of our model considering constant acceleration vector. And based on this derived kinematic equation in a vector form, we discuss the motion in two-dimensional space with constant acceleration, which is the classical example, projectile motion at some angle to the horizon. So next time we will consider another type of motion in two-dimensional space, which is rotational motion. And that is one of also very important examples which you will deal quite often with in the future. So thank you very much for attention and see you next time on Friday.